Thank you for downloading this podcast from The Reedy Clubby Show on Talk Radio 702 and 567 Cape Talk. For more, please go to 702.co.za or capetalk.co.za. Talk Radio 702 and 567 Cape Talk. The Naked Scientist.
Chris, good morning.
Morning.
Lovely to be with you. So we get a lot of questions about the Big Bang. And right now you're saying that there's a breakthrough that has been announced. Tell us about it.
Well, the big news this week, Reedy, is that scientists reckon that they've got evidence for what we call gravity waves. And this is a piece of research which has been published so far in Archive, which is an online repository for science, which is just in the process of coming out and being checked and being distributed to people to see what they think of it. And this group, led by John Kovac in the States, have been collecting data for the last couple of years from Antarctica using a telescopic instrument called BICEP-2. And it is a powerful instrument. BICEP actually stands for Background Imaging of Cosmic Extragalactic Polarization 2, which is probably why they call it BICEP-2. But this instrument is designed to study something called the cosmic microwave background radiation. This is radiation left over from the Big Bang that created the universe about 13.8 billion years ago. And because the universe has inflated and expanded to the proportions it now has and is continuing to grow, the radiation, which was very short wavelength back 13.8 billion years ago, has been stretched out to make these microwaves, which we can now pick up. And written into those microwaves are what we call polarizations or twists, which reflect what was going on in the very earliest phases of the Big Bang. And that's what this group have been able to see and publish this week. And why this is important is that although we can see light from the very early universe, we can only see light after this initial phase when the universe cooled enough for atoms to form and things to become transparent. In the very early phases, it was completely opaque because it was ionized. There was no way that signals could get through because there was no way atoms could stably exist. Now, by looking at these wave patterns written into this afterglow of the Big Bang radiation, we can begin to infer what must have happened during that very early era, which has left us with the structure of the universe that it's evolved into today. So it's a big breakthrough. It does need, obviously, corroboration and confirmation, but the data they've collected is more than 2 years old. So, in other words, they've been collecting this data for a long time and checking it for a long time to make sure they haven't got it wrong.
Very fascinating indeed. I have a tweet here from Dudzi who asks, if humans evolved from apes, has the process stopped? Do we still have humans evolving from apes?
Well, let's just sort of clear this up very slightly, because it's not strictly true to say humans evolved from apes in the modern sense of the word ape. We didn't suddenly have monkeys that turned into humans. What actually happened is that roughly 6 million years ago, human ancestors and ape ancestors were the same thing. And the two split apart and began to evolve down separate lineages or pathways. And though that common ancestor therefore gave rise to the apes that we have today and the humans we have today. And along the way, there were various other offshoots. We know that there were many species of early human, and many of them actually have been discovered in South Africa. And up until very recently, there were perhaps 2 or 3 other species of human living alongside us, Homo sapiens, because there were Neanderthals and the Flores people, the little hobbit people. So it's not strictly true to say that apes turned into us. Apes' ancestors turned into us and apes, and the same processes that are leading to that evolution that happens over the last 6 million years, those processes continue today. So everybody and everything is still evolving in response to pressure exerted by the environment. So yes, it's absolutely still happening.
021-446-0567 or 11-883-0702. Granville in Germiston. Hi.
Hi.
Yes, I got my question from last week.
Oh.
So we are on about 5,500 feet above sea level, and I've checked what temperature water boils on my stove, and it's 95 degrees. If you want to make a kind of biofuel or something, what temperature does alcohol boil at this altitude?
Hi, Granville. Very interesting question. the reason that the water boils at a lower temperature is if you think about the atmosphere as being like a giant stopper in the bottle. It's applying a pressure to the surface of the liquid. If you want to make something boil, you've got to make the particles have enough energy so they're moving sufficiently fast or shaking sufficiently hard to break the bonds between the particles. And water molecules are very sticky. They stick to each other by hydrogen bonds. But if you give them enough energy, in other words, energy equivalent to roughly 100 degrees C of heating, they're vibrating or moving sufficiently fast that they can sever those bonds to each other, and they can exist as individual water molecules in the form of a vapor, and they then go pinging off as steam. If you reduce the atmospheric pressure above the liquid, it's not pressing as hard into the surface of the liquid, and therefore the water molecules don't have to have as much energy to break the bonds to the other water molecules and also surmount that pressure to escape as a gas. And therefore, the higher you go, the lower the boiling point will be for a liquid. And it's going to be the same for alcohol. Alcohol will boil at a lower temperature because the alcohol molecules are going to stick to each other less hard. Alcohol already boils at a lower temperature than water because the molecules are bigger and less sticky than water because they've got a carbon chain in them which doesn't stick to other chains as easily as water molecules stick to other water molecules. So alcohol already has a lower boiling point, and as you drop the as you drop the pressure, therefore the alcohol boiling point will get lower and lower as well. So yes, your alcohol will boil off slightly lower temperature in Johannesburg than it will in, say, Cape Town.
Okay, thank you very much, Granville. I think I'm going to try that experiment. It must have the same effect on me as the cold. But let's go to, is it Munia in Pretoria? Hello?
Hi, Rudy and scientist. I was just wondering, I listened to your program last week. You were discussing the processes, comparing a computer processor and a human brain.
Yes.
I was wondering, since the human brain sounds like it's a much better processor, more powerful, would it be possible to hardwire a human brain to actually power and run a computer?
People are doing that, in fact, and in the last few years, scientists have managed to build a flight simulator controlled by rat brain cells. They made a dish with the brain cells in, and they connected the nerve cells together by letting the cells be growing in the plate together, so the cells put out connections to each other, and then they read the signals, the electrical activity of the nerve cells, and interpreted that into an interface into a computer so that the brain in the dish was effectively flying a simulator. So that's an early step. But yes, people are beginning to develop much more, or much better, these so-called brain-computer interfaces now, because this may be one way in which we can restore movement to people who've become paralyzed or have brain injury. It may also be a better way of getting information into our nervous system. There's a guy called Kevin Warwick who works at Reading University in Britain, and he was the first official human cyborg. He had an implant put into his nervous system so that he could effectively read his nerve activity into a computer, and the computer could inject nerve activity into him. And he said he quite enjoyed the experience because it gave him an extra means of gaining and expressing information in and out of his body.
Thank you very much, Munia. Thank you. Simon in Pretoria, hi.
Hi, how are you?
Very well. Your question to the Naked Scientist?
Yes, I just want to find out how far should one build a house away from our ESCOM lines? The ESCOM lines are the one that transmit energy from power station to electricity, from power stations to household and industrial area. And number two is will the magnetic flux from the lines, the magnetic flux from these lines affect the appliances in the house?
Okay.
Two interesting questions. First of all, how far away? Well, we're not clear that there's any health impact of power lines anyway. The jury's out on this. They've done lots and lots of studies and there's lots and lots of experiments. There's one suggestion that people who are subject to very intense electrical fields for long periods of time, and specifically they've looked at train drivers of electric trains for this, because obviously you have high-tension cables above the trains and the driver is therefore in that field in the course of doing his or her job continuously for their working lifetime. There's a suggestion that there might be some impact on the body in those individuals, but at the same time, it might just be what we call statistical noise. So there's no clear answer here in terms of the safety of transmission lines. There was a report the other day that suggested that there may be ultraviolet light coming off of transmission lines caused by the ionisation of air in that intense electric field around very high-powered lines, and that whilst humans probably can't see that and are probably not affected by it, other wildlife can see it because some animals are sensitive to UV, and that this may in fact have an impact behaviourally and perhaps from a health point of view on those animals. In terms of the magnetic flux, we don't think there's any evidence of harm here, and in fact that's why magnetic resonance imaging, the scanners that you can get in the hospital to see inside the body in unprecedented detail, they're regarded as much safer than their predecessor, which was the CT scan, which uses X-rays, because X-rays are ionising radiation, and we don't have any evidence that magnetic fields pose a significant health threat to us. But at the same time, we're still gathering data. So come back in another 10 years and we might have a clearer answer for you.
Thanks, Simon. Here's an SMS here, speaking of electricity and stuff. Do people who sleep with lights on put themselves at risk of getting insomnia and skin cancer from the light of their bedroom light bulbs? An SMS.
Well, first of all, let me reassure you that leaving the light on is not a risk factor for skin cancer. That isn't going to happen, thank goodness, because the light coming from a normal light bulb is infrared heat plus some visible spectrum light, and that visible spectrum light is too low in energy to damage your DNA, which is what needs to happen for you to be at risk of skin cancer. So it's not going to do that. But there may be behavioural effects. And we know that the human eye contains cells which are intensely sensitive to light of certain wavelengths, but it doesn't use those cells to see with. It uses those cells to inform the body clock what time of day it is, and the body clock is in your brain. And therefore, if you are exposing yourself to light at funny times of the day and night when your body should be asleep, you could be resetting your body clock or sending some degree of resetting signal into your body clock, and this could lead to poorer sleep. So therefore, it might be worth considering, if you are feeling like you're suffering from disturbed sleep, condemning leaving the light on, and maybe sleeping in a darker room might make sleep quality improve, and that will make you feel better.
I have a question here about seeing red. I read something that angry people really do see red where others don't. And this is a discovery by scientists. What do you think of this, Chris? Do we see red when we're angry?
Well, there's quite an interesting thing about the whole effect of colour in evolution and also in sport, because people did studies in the last 10 years or so looking at which colour people in the Olympics played in and whether or not they won their event. Mm-hmm. And people who play in red win significantly more often than people who play in other colours. And there was a lovely study looking at Greco-Roman wrestling, for example, and the competitors played in either blue or red, and the red player was successful more often than they should have been by chance. Why should this be? Well, nature has chosen to use the colour red as a strong visual signal that we're annoyed. And if you look at when someone gets angry, they tend to go red in the face, and this is because you dilate up blood vessels close to your skin in your face, increase the flow of blood through your face, and this gives out a lot of red colour because the blood is close to the skin surface and reflects a lot of red light, so other people see you're red. And this gives out the sign that you're angry. And it seems that when people see these signals, it puts other people on the back foot a bit and they become more defensive. So if you therefore present a big red surface to somebody in the form of wearing a red costume, actually this can be a big advantage to you because other people are therefore intimidated without realising it, and they're more likely to succumb to your maybe your demands. So yes, the colour is definitely important, but whether or not people actually are seeing more or less red, I'm not sure about that one.
Let's go to Vanessa. Vanessa in Sandton. Good morning.
Good morning, Rudy. I would just like to ask the naked scientist, when you're drawing up medicine in a syringe and the medicine is calibrated to 1 ml, how much fluid is left in the hub of the needle, or is it calibrated accordingly to the 1 ml? Are you drawing up extra fluid, or is that 1 ml in total?
Hi, Vanessa. Now, you raise a very good point. If you are doing this in a chemistry laboratory with high precision equipment and a beautiful pipette, which has all been calibrated to be used at a certain temperature, and it's got a meniscus line on it and all that kind of thing, then this is taken into account so that you get just the right amount of fluid coming out of your pipette. In a healthcare setting with a needle, and a syringe, then you already have got such huge errors owing to the thickness of the line on the side of the syringe and your line of sight not being spot on. And some people put a tiny orange needle on the syringe, others will put one of those big green ones on. This is not taken into account unless you use a specified giving set or calculate these things appropriately. Most of the time, there's enough degrees of freedom in how you administer these agents that actually the tiny amount that's left in the needle or not really isn't taken into account. So there will be a big variation between one person and another. So it would have a chemist turning in their grave if they were doing precision analytical chemistry. But from a healthcare point of view, it doesn't make any difference because there's a degree of safety margin anyway written into how all these drugs work and their effects. So you've raised a very good point, but it's probably not clinically that relevant.
Here's an SMS here. Why do I feel dizzy when I spin?
Well, the reason for that is that your ears have inside them, in your inner ear, your vestibular apparatus. And the vestibular apparatus are a series of what we call semicircular canals. These are small, roughly small coin-sized circles which have fluid in them. And they're arranged at 90 degrees to each other. So you have one which is like a flat plate sitting on top of your head. If you imagine you put a plate on your head, that's the orientation of one of them. The other is if you turned that plate so it was lifted up, so it was edge onto the top of your head, that would be the orientation of the other one of these circular canals. And the other one is if you then turned the plate so it was going back to front, from front to back of your head on its side, that would be the other orientation. In other words, you've got a circle which is in all three axes that you could move your head. Projecting into those little tiny tubes are a series of hairs called hair cells. And when you move your head, the fluid, because the fluid is not attached to the sides of the semicircular canals, the fluid is momentarily left behind while your head moves. Mm-hmm. And this causes the fluid to displace or push on the hairs, and the hairs are connected to nerve cells, which then tell the brain the fluid in whatever one of these three axes is moving in a certain way, and the brain then resolves the contribution of the different canals to work out what direction you must be moving in each of the three axes, side to side, back to front, and so on. And it then integrates all of that information to then, tell your eyes where to go, so your eyes oppose the movement of your body so you can maintain steady gaze, and it controls your musculature so that you balance by moving your muscles to oppose the movement that your body's undergoing, and that keeps you standing up straight. Now, you can fool that system by spinning round and round and round and round and round, because what happens if you keep moving in the same direction is that slowly the fluid, because of friction between the fluid and the wall of the canal, the fluid begins to spin. And the fluid then starts or ends up turning at the same rate you are. If you then stop abruptly, your bones of your head stop moving, but the fluid has still got momentum, so the fluid carries on moving. Mm-hmm. Now it's pushing on those hairs again, and the hairs think, you must be moving the opposite way to the way you actually are. You're staying still, but it thinks you're still moving. So all of those protective reflexes to keep you standing up straight and keep your eyes balanced all kick in, but in fact, then they're kicking in to stop you falling over when you're not actually falling, so they actually make you fall over.
Fantastic. Chris, lovely chatting to you. We'll speak to you again next week.
Yeah, I hope so. See you soon, then.
Cheers. Bye-bye. That's Chris Smith, our naked scientist, and we will podcast this conversation.